This machine has two moving parts: no motor, no fuel, no solar panel, no electricity of any kind, anywhere in it. You put it beside a stream, and it lifts water uphill, not for an hour, continuously, day and night, through winter, for decades. There are examples of these still running on British estates after more than a century of service, and there are companies that have been manufacturing them without interruption since the 1820s. It was invented in 1796 by the man who built the first hot air balloon. And here's the honest part, stated up front, because almost nobody covering this will say it. This machine only works if you already have falling water. It needs a stream with a genuine vertical drop, and if your land is flat, no version of this will do anything at all. That is the entire gatekeeper, and I will give you the two measurements that settle it in about 20 minutes. There is a second honest number too, and it surprises people. Roughly 90% of the water that enters this pump comes straight back out of it and returns to the stream. Only about 10% goes uphill. That sounds like a terrible machine until you understand what it costs to run, which is nothing forever. And then the arithmetic looks completely different. Let me start with how it works, because this is one of the most satisfying mechanisms in engineering, and it runs on a phenomenon most people only know as a problem. You have felt water hammer. It is the bang in your pipes when you shut a tap quickly, and it happens because moving water has momentum. A column of water traveling down a pipe is heavy, and it is moving. And when you stop it suddenly, all of that momentum has to go somewhere. It converts instantly into a pressure spike, and that spike is powerful enough to burst pipework, which is why plumbers spend real effort suppressing it. The hydraulic ram does not suppress it. The hydraulic ram is a machine built entirely around causing it deliberately, thousands of times a day, and harvesting the result. Here is the cycle, and there are only 4 steps. Water flows from your source down a rigid drive pipe and out through an open valve at the bottom, which is called the waste valve. Nothing useful is happening yet, and the water is simply running out onto the ground. But as it flows, it accelerates, and once it reaches a certain speed, the force of that moving water pushes the waste valve shut. Suddenly, now the entire column of water in that drive pipe has been stopped dead, and its momentum has nowhere to go. So it produces a violent pressure spike, exactly the water hammer you have heard in your house. That spike is far higher than the pressure the water arrived with, and it forces open a second valve, the delivery valve, pushing a slug of water into an air chamber and up the delivery pipe. Then the pressure collapses. The delivery valve closes. The waste valve falls open again, under its own weight. Water starts flowing, and the whole thing repeats, somewhere between 30 and 100 times a minute, all day, all night, forever. The air chamber is worth a sentence because it is the component people leave out and then wonder why their pump destroys itself. It is a sealed volume of trapped air above the delivery valve, and it acts as a spring. Without it, each pressure spike would slam into a solid column of water in the delivery pipe with nothing to absorb it. With it, the air compresses, cushions the blow, and then pushes the water smoothly up the hill between beats. So the whole machine is a drive pipe, 2 valves, an air chamber, and a delivery pipe. 2 of those parts move, nothing else does, and it runs on the one thing you already have, which is water falling a short distance. Now the arithmetic, because this is what tells you whether it works on your land. There is a rule of thumb that has been used for 2 centuries, and it is close enough to be genuinely useful. A hydraulic ram will deliver roughly 10% of the water flowing into it to roughly 10 times the height it fell. So if your source falls 6 feet down to the pump can push water up to somewhere around 60 feet above itself. And of every 10 gallons that enter, about 1 gallon goes up the hill, and about 9 leave through the waste valve. Now look at that 10% honestly, because the reaction is always the same, and it is the wrong reaction. 10% sounds dreadful, but the 9 gallons are not destroyed. They flow straight back into the stream a few feet below where they came from, which is exactly where they were going anyway. You have not consumed them. You have borrowed their momentum, and the 1 gallon goes uphill every single minute of every day, with nobody present and nothing to pay. 1 gallon a minute is 1,440 gallons a day. That is a meaningful household supply, a livestock trough that never runs dry, and irrigation for a serious garden, delivered by a machine that does not know or care whether it is Tuesday. That is the number people miss. The rate is small. The total is enormous, because it never stops. which points at the single most important design decision in any RAM installation. And it is not the pump, it is the tank. Because the delivery rate is slow and constant, while household demand is fast and irregular, the correct arrangement is always the same. The RAM fills a storage tank at the top of the hill, quietly, around the clock. The house draws from that tank whenever it likes, at whatever rate it likes, under gravity. The pump never has to keep up with a shower or a hose, since it is filling a reservoir rather than supplying a tap directly. That is exactly how every Victorian estate installation was arranged, with a header tank in the roof or on the hill. And it is why those systems felt like ordinary plumbing to the people using them, despite being fed by a machine. Delivering a trickle, size the tank for a day or two of your household use, and the slow rate stops being a limitation at all. And it is worth naming what those daily totals actually cover, since the figures are more useful than they sound. Livestock is the classic application, and the easiest, since a trough that refills continuously never runs dry, and nobody has to haul anything. A few hundred gallons a day waters a serious number of animals. Irrigation is the next, and a RAM feeding a tank that gravity feeds a drip system is close to the ideal arrangement. Since drip irrigation wants exactly the slow, steady pressure a header tank provides. Household supply is entirely achievable at the upper end of these numbers, and it is what those Victorian installations were doing. And there is a use that costs nothing extra, which is fire protection. A full tank sitting above a property, fed continuously and independent of any pump or power supply, is a genuinely valuable thing to have in dry country. And it is there whether the grid is up or not. So the obvious question is, who built this? And the answer is genuinely delightful. In 1772, an English clockmaker and engineer named John Whitehurst built a device using this principle to lift water for a house. But his version needed a person to operate the valve by hand. Then, in 1796, in France, Joseph Michel Montgolfier made it automatic. That name should be familiar. The Montgolfier brothers built the first hot air balloon and put the first humans into flight in 1783. 13 years later, one of them worked out how to make a valve close itself and turned a hand-operated curiosity into a machine that runs unattended forever. He patented it, a British patent followed, and by 1809, a United States patent had been issued. Within decades, the hydraulic ram had spread across Europe and America. And then it did something very few 19th century inventions managed. It stayed. In England, the firm of Green & Carta has been manufacturing hydraulic rams since the 1820s, and their pumps are still made and sold today. In Pennsylvania, the Rife Hydraulic Engine Manufacturing Company was founded in 1884 and has been building rams continuously since. Read those dates again. These are companies that have manufactured the same fundamental machine, uninterrupted for well over a century, through 2 world wars and the entire electrical revolution. That does not happen to bad technology. Now the deployment, and it is worth seeing at 4 scales, start with the estate scale, which is where most surviving examples live. Through the 19th century, country houses and farms across Britain and Europe installed rams in their streams to supply the house, the stables, and the gardens. Many of those installations ran for 100 years or more, with nothing but occasional valve maintenance, and a number of them are still in service, which is why enthusiasts can go and photograph working Victorian pumps. Consider what that meant to a house in 1860. Running water indoors was a luxury, and getting it there without a municipal supply meant either a well and a hand pump or somebody carrying it. A ram in the stream below the house changed that completely. It filled a tank in the roof space continuously, and from that tank the household had water at a tap, under gravity, at any hour. With no servant carrying anything and no engine to be fired up and tended. For a large country house, that was the difference between modern plumbing and medieval plumbing, delivered by a machine that consumed nothing and was checked perhaps twice a year. And the reason so many survive is precisely that nobody had a reason to remove them. They sat at the bottom of a field, knocking away, long after the house was connected to mains water, and in many cases, the family simply forgot they were there. Then the American farm scale. Before rural electrification, an enormous number of American farms with a creek and a hill used a ram to get water to the house and the stock tank. And there are still rams running quietly on properties whose owners inherited them and simply never had a reason to stop. Then the development scale, which is where the technology is genuinely alive today. Ram pumps have been installed in large numbers across Nepal, the Philippines, Indonesia, and parts of Africa, supplying villages that sit above a water source with no grid to run a pump from. Organizations promote them specifically because they can be built and repaired locally. They consume no fuel, and there is no operating cost at all. And then the modern off-grid and permaculture scale, where the ram is treated as a piece of standard equipment for anyone with running water and elevation, for exactly the reasons it always was. So here's the question in the title, and the answer is not a conspiracy. Electricity buried it. In the United States, the Rural Electrification Act of 1935 began running power lines to farms that had never had them. And within a couple of decades, the transformation was close to complete. The same thing happened across Europe on its own timetable. And the moment a farm had a wire, the calculation changed completely. An electric pump can be installed anywhere, including places with no fall at all. It can be sized to deliver whatever you want, rather than 10% of a stream. It fits in a small box. It needs no drive pipe running down a hillside. It requires no tuning, and when it breaks, you buy another one. Against that, the ram asks for a specific piece of landscape, a pipe run, and an afternoon of adjustment. So farms stopped installing them. Manufacturers shrank to a handful. And the knowledge went out of general circulation within about a generation. Not because it failed, because a wire made it unnecessary for anyone who had a wire, which is precisely why it survived in the places where the wire never arrived, and why it is coming back among people who would rather not depend on one. This channel exists for exactly this kind of straight answer. One honest method a week, and subscribing is how those keep arriving. Now the two measurements that decide everything, and you can take both this weekend for nothing. The first is fall, meaning the vertical drop from your water source down to where the pump will sit. This is vertical height, not distance along the ground, and it is the number that makes or breaks the project. You want a minimum of somewhere around 1.5 to 3 feet to run at all, and considerably more is much better, since your delivery height scales directly with it. Measure it with a length of clear hose filled with water, leapfrogging down the slope, or with a laser level. The second is flow. Find or make a point where the stream funnels through one channel and time how long a bucket of known volume takes to fill. Most home rams want a couple of gallons a minute as a working minimum, and more gives you more. Then run the rule of thumb. 10% of your flow to 10 times your fall, and you will know within a few minutes whether this is worth building. Let me work one example through properly, since the abstraction hides how good the numbers can be. Say you measure a fall of 8 feet from your source, down to where the pump would sit, and a flow of 6 gallons a minute in that stream. 10 times your fall gives you a delivery height of roughly 80 feet, which is comfortably enough to reach a house or a tank well up a hillside. 10% of your flow gives you roughly 0.6 of a gallon a minute, arriving at the top. Now multiply that by time, which is where this machine wins. 0.6 of a gallon a minute is 36 gallons an hour, which is 864 gallons a day, which is over 300,000 gallons a year. From a creek you can step across, delivered to a tank 80 feet above it by a machine with 2 moving parts and no bill attached to it. And if your numbers are smaller than that, the machine still works. It simply fills the tank more slowly, which matters far less than people expect when the filling never stops. And measure in your dry season exactly as with any water project, because a stream that vanishes in August will give you a pump that fails precisely when you need water most. Now the build? The drive pipe is the most important component and the one people get wrong. It must be rigid, meaning steel, or Schedule 40 PVC, and it must never be flexible hose. The reason is the whole mechanism. Water hammer only happens if the water column is stopped hard, and a flexible pipe simply swells and absorbs the shock, which means no pressure spike and no pumping. A garden hose as a drive pipe produces a machine that sits there dribbling. Length matters too, and the traditional guidance is a drive pipe somewhere between 5 and 10 times your fall height, which gives the water column enough mass and length to generate a proper spike. The waste valve is your first moving part, and it takes the beating. This is the valve that slams shut thousands of times a day, and it is where every ram eventually needs attention. Home builders typically use a modified swing check valve or a purpose-made weighted valve, and brass lasts dramatically longer than plastic here. The delivery valve is your second moving part. usually a spring check valve, and it needs to open under the pressure spike and close cleanly afterwards. The air chamber is a capped length of pipe standing above the delivery valve, and bigger is generally better since more trapped air makes a softer spring. And there is one small component that almost every first build omits and every experienced builder insists on: the snifter valve, which is nothing more than a tiny hole with a small check valve, positioned so that a little air is drawn in on each cycle. Without it, the air in your chamber gradually dissolves into the water and disappears. And within days, you have a chamber full of solid water, no cushion, and a pump that hammers itself apart. That tiny hole is the difference between a machine that runs for years and one that cracks a fitting in a fortnight. Total build cost lands somewhere between $50 and $150 in PVC, and rather more in brass, which is what you want if you intend to leave it running unattended for years. If it will not start, and plenty do not on the first attempt, work through 4 things in order. The waste valve may be too heavy to close, so lighten it and try again. This is the most common cause by a wide margin. The drive pipe may be too flexible or too short, which means no proper hammer, rigid, and 5 to 10 times your fall in length. There may be air trapped in the drive pipe, so make sure it runs downhill consistently without a high point where a bubble can sit, since a pocket of air absorbs the shock exactly like a flexible pipe does. Or your fall may simply be too small, which is the one that cannot be tuned around, and once it is running, most rams that stop later do so for one of 2 reasons. Either the intake screen has clogged, which is the ordinary autumn problem, or the air chamber has waterlogged because the snifter hole blocked. Both are 5-minute fixes once you know to look for them. Now, the section the sponsored videos skip, because this has real limits. The first is the gatekeeper I have already given you: no fall, no pump, and there is no clever workaround. The second is that 10% delivery ratio, which means a ram is unsuitable if you need most of the water from a small stream, since the majority is going back to the creek regardless. The third is tuning, and this is the part nobody mentions. A ram has to be adjusted, meaning the weight or spring on the waste valve is set so the valve closes at the right moment. Too light and it slams shut too early, wasting the stroke. Too heavy and it never closes at all. Every builder spends an hour with a wrench getting the beat right, and the machine tells you when you have it, since it settles into a steady rhythm you can hear from a distance. That tuning process is worth describing because it is the part where most first-time builders give up too early. Start with the waste valve as light as it will go, and the pump will run very fast, snapping shut almost immediately each cycle. It sounds busy and it delivers very little because the water column never gets up to speed before the valve closes. Now add weight or increase the spring tension a little at a time. The beat slows, each stroke gets stronger, and the delivery rate climbs. Keep going and you will pass the optimum, at which point the valve becomes so heavy that the flow can no longer lift it closed and the pump stalls completely, sitting there with water pouring out of it and nothing going up the hill. So the method is simply to walk it from too fast to stalled, note where the delivery was strongest, and set it just below that. Most working rams settle somewhere between 40 and 80 beats a minute, and owners genuinely learn the sound of their own machine. A ram that changes its rhythm is telling you something has changed, usually a partially blocked intake or a dropping stream. That is the closest thing to a maintenance schedule this machine has, and it costs nothing but listening. The fourth is debris, which is the actual daily job. Your intake needs screening, and leaves in autumn are the recurring problem exactly as they are with any water system. The fifth is freezing, since a ram sitting in an open stream in a hard winter is full of water in exposed pipework, and cold climates require burying, insulating, or seasonal shutdown. And the sixth is noise. This machine works by banging, and it bangs continuously. From a distance, it is a pleasant rhythmic knock that people who own them describe with genuine affection, and directly outside a bedroom window, it is not. Now the safety section, which is short but real. Water hammer is genuinely violent, and that is the entire operating principle here rather than an accident. Use pipe and fittings rated for pressure. Use rigid drive pipe, and do not improvise the pressure-bearing parts out of thin plastic that was never intended for it. A ram that fails does so with a bang and can throw fittings. The air chamber is a pressure vessel and should be treated as one, meaning sound construction and a cap that will not blow off. Anchor the pump properly, since a machine that is hammering 30 to 100 times a minute will walk itself across a stream bed if you let it. And check your water rights before you divert anything. In much of the country, and especially across the western states, the water crossing your land is not automatically yours to take, and a diversion may require permission. It costs nothing to ask and a great deal to find out afterwards. The ledger for the whole story then: drive pipe, priced by the foot, and usually the largest single item. To check valves, $20 to $60, depending on brass or plastic. Air chamber fittings, $10 to $30. Delivery pipe, priced by the foot, and cheaper since it can be smaller and flexible. Total, $50 to $150 for a machine that will move water uphill continuously for the next 20 years without a bill, a battery, or a service contract. Here's the thing worth keeping from all of it. In 1796, the man who had put the first humans into the sky worked out how to make a valve close itself and produced a machine that has been manufactured continuously ever since by companies founded in the 1820s and 1880s. It has no motor, it consumes nothing, and it runs on the banging in your pipes that plumbers spend their careers trying to eliminate. It did not lose to a better pump, it lost to a wire, and a wire is a genuinely wonderful thing which most of us would not give up. But the wire also did something quieter. It made a whole category of machines unnecessary, and unnecessary things stop being taught within about one generation. There are properties in this country with a creek, a hill, and a house, whose owners run an electric pump and pay for it every month. Standing 100 feet from where a Victorian farmer would have installed something that never asked for anything again. Everything this channel has gathered on moving and storing water without the grid, the pumps, the catchments, the real numbers, and the real limits, lives in one place, linked right below, and the comments are the missing map. Do you have running water on your land, and is there any fall to it? Give me the numbers if you have them, because half the people watching this are standing on a site and have never once thought to measure. As for the tower that pulls drinking water straight out of the air, with no well, no rain, and no power at all, that is on screen right now. Same problem, stranger solution. Till next time.